Hello, welcome to Group 6 project, senior design project called Photonica, which is a laser harp without mechanical strings. I'm Daniel Balaskita, the project leader for this midterm demo. For project overview, traditional harps we find are large, fragile, and can be difficult to play. But for this project, we want to use lasers to replace the strings, and it'll be accessible for those who have limited mobility. A frameless design emphasizes portability and inclusivity, and it will combine optics, embedded systems, and electronics in one device. So for the engineering requirements, we first wanted to achieve a response time that is less than a quarter of a second. And essentially, what this means is the time between beam disruption and sound playing. This response time should be less than 25 seconds for it to not be too noticeable for the user. Number of strings should be 7. For the next thing, the memory, we're planning to use something less than 80 gigabytes. And for the cost, it will probably a high power will probably be $500. And for the spacing of the strings, we want at least 0.5 inches. Next, for the detection accuracy, we want it to be 90 to 99%. And this will just mean how often the beam disruption will be detected. Essentially, it will be between 90 to 99%. For the power consumption, we want it to be less than 200 watts. And this is for the entire unit, all right? So for the clock speed processing, we're planning to have it less than 10 megahertz. And this is just something standard that will be for the ESP32. And for the weight, it will be 5 to 25 pounds. And then finally, for the size, it's going to be 1 to 2 cubic feet. For the project blueprint, we want to have a product that has a LCD screen to show the current octave of the harp, and then also a dial for the volume. In addition to that, we want to have the lasers on top, and then two pedals for button inputs. For one being to change the key, and one to change the octave. And essentially, the chassis for the project will be 3D printed.
So now we have the optics subsystem overview. We have the laser, which is going into the collimating lens, then the negative lens, and then the positive lens. This will collimate the beam and then expand it to the desired beam width. It then goes into the mirror that's attached to the stepper motor. Then through the slits, there's 7 slits to produce the 7 beams. And then you can see the one beam at the end. It's important to note that this is not the laser that's going to be used in the final project, and the collection lens is not shown in this image, but it is in the videos later in the presentation.
For this midterm demo, we will be testing all the major components that will be used for our final prototype. This includes a transimpedance amplifier and the photodiode to detect any interruptions in the laser, DF player mini and the speaker to play noise, the stepper motor, and the driver to create the beam fan and all the power components, as well as the 12 volt wall outlet and the 2 regulators.
For the audio, for this midterm, we finally got our Dayton Audio RS100 4.4-inch speaker, which has a frequency response of 80 to 20,000 hertz, and this can explain for a clear and minimally distorted sound of the speaker, especially for the low notes, which is really what we want for a good harmonic sound with it. And then next, for the amplifier of the DF player, we used the amplifier of the DF player for this midterm as well. For the software design, to implement the Harp functionality, it will involve multiple components, such as if functions for controlling mechanisms and photo detection, a counter function to know which position of the stepper motor and laser for which note to play, and an update function for the LCD. In the software design in the midterm, the multiple cores and simultaneous task feature of the ESP32 was used to simultaneously use the DF player and stepper motor in tandem. For this midterm, the main loop will be used on core 1 for the stepper motor and photo detection, and a separate task on core 1 will be used for the audio and playing the respective note.
These are some of the components that we're going to be using for our midterm demo. It includes a transimpedance amplifier and the photodiode in breadboard and PCB. We have the two voltage regulators, and then we have the laser module, which will be isolated from the rest of the system. The listed components also include the ESP module that's going to be controlling every component, the DF player and the speaker, and the stepper motor and stepper motor driver that will be used to create the beam fan.
This video demonstrates the beam fan setup that we'll be using to showcase the 7 laser strings in our project. As you can see, we start with a single laser beam that's directed toward a mirror attached to a stepper motor. When the stepper motor rotates, the mirror changes the beam's reflection angle. The reflected beam is then projected through a slit plate that contains 7 evenly spaced openings. As the mirror moves, the laser light passes through these slits, creating 7 distinct laser beams that form a fan-like pattern. This design allows us to simulate the appearance of multiple laser strings using just one laser source. Each of these beams will later correspond to a different musical note when paired with the photodiode detection system and audio module. The following video demonstrates the accuracy of the laser and photodiode detection system working simultaneously. As shown in the following clip, a single laser beam is directed toward the stepper motor equipped with a mirror mount attachment. When the laser beam is deflected using a note card, the running code displays the photodiode's detection of the beam deflection through the collection lens. The next video highlights the audio component of the project. As shown, when the photodiode detects a deflection of the laser beam from the collection lens, a corresponding musical note is played.
As you can see here, we have the LCD screen to display the current volume. Right now it's at 0, but when we raise it, you can start to hear it, and it will be automatic as well. So that way it's synchronous with the audio. Nothing is blocking the audio. And this will be the same for the other controlling mechanisms of the system.
This test was used to highlight one of our engineering requirements, which is the response time. It was used to determine how many seconds it took between beam disruption to photodiode detection to then a note being played from DF mini player to speaker. Our average detection was 0.16 seconds. This test shows our second engineering requirement, which is detection accuracy. It was used to determine the accuracy of collection lens and photodiode detecting a laser beam disruption. We had an average detection of 90%.
This is an overview of the power consumption of the entire system. This is going to be one of our engineering requirements, that we have to be lower than 200 watts. It seems like we're going to pass that quite well, but overall, the overall power drawn from the wall was 3.48 watts, and total power consumed by the components was about 2.4, which is about 60% efficiency. We had pretty good efficiency from the regulator as well. That relatively low efficiency probably has to do with the amount of wires and the breadboards used. So in the final project, we'll probably have a higher efficiency and higher output, higher total power consumed by the components. Overall, we were successful in passing the engineering requirements that were listed at the beginning. There's probably going to be some changes from this midterm demo to the final midterm demo. First, the main board was not used, so we had to use the ESP32 on a breadboard. Additionally, we had some problems with the transimpedance amplifier PCB, so we had to also construct that into a breadboard. That included a lot of wires, which would create noise and things like that. There would probably be an inclusion of more than one photodiode in the final project to ensure that we're getting an interruption in the laser. User interfacing will also be shown in the final project. All the buttons, all the switches, all the pedals will also be included, and the laser module will be fully integrated into our final project as well.
For a final software design after this, we want to try to use that next core and task of the simultaneous function to be used for the controlling mechanisms and updating the LCD. In addition to that, we want to add a boot up procedure and booting down procedure for the system. In addition, we need to have a proper workflow and task organization of the software design that will allow for a responsive and functional laser harp.